You good? Okay, guys, so we're just going to go ahead and get started. First, I just want to say that I took all of these questions from either Dr. Conacher's practice problems, Dr. Saha's practice problems, or the book, so everybody should be able to find stuff rather easily. So let's just get started with the first question. An aluminum nail has an excess charge of 3.2 microcoulombs, and we want to know how many electrons must be added to the nail to make it electrically neutral. So whenever we see how many electrons, we know we're going to use this formula, Q equals NE, where Q is the charge, N is the number of electrons, and E is the charge of an electron. So remember that E is equal to 1.6 times 10 to the negative 19 coulombs. And we can just use algebra. N is going to equal Q over E. They gave us the charge, 3.2 times 10 to the negative 6 coulombs over 1.6 times 10 to the negative 19 coulombs. And when you do that math out, you should get 2 times 10 to the 13. And remember that these will not have units because we're looking for N, and N is unitless. You're canceling out those coulombs. Okay. So on to the next one. What is the magnitude and direction of the electric force on a negative 3 microcoulomb charge? So Q is equal to negative 3 times 10 to the negative 6 coulombs at a point where the electric field is 2,800 newtons per coulomb and is directed along the positive y-axis. So we are wanting to find the force. Oh, my hair. So we know we have an equation, F is equal to electric field times charge. We're just going to be, this is another just plug and chug problem. So we have negative 3 times 10 to the negative 6 times 2,800. Okay? And that will end up giving you 0.0084 newtons, which we know already. We can kind of already see it's going to be C. But it's also going to be in the y direction, in the negative y direction, my bad, because we are accounting for that negative in the charge, and we're going to bring it down here, and that'll show us that it's going in the opposite direction in which it started. So let me kind of write that a little clearer. Negative 0.0084 newtons. So if we were starting in the negative y, going to the negative y-axis, and we got a negative number, it would now be going positive direction. Okay. So number 3, a parallel plate capacitor has a potential difference between its plates of 1.6 volts and a plate separation difference of 2.5 millimeters. What is the magnitude of the electric field if a material that has a dielectric constant of 3.4 is inserted between the plates? So we know we have V is equal to 1.6 volts. Our distance is 2.5 times 10 to the negative 3. We want everything in meters. And our dielectric constant, it's kind of a cursive K a little bit, that is 3.4. And we know that our electric field is equal to our peak electric field over our dielectric constant. That is a formula that should be on your formula sheets. And the peak electric field is also equal to voltage over distance. So we can kind of plug that in. So this problem is more about just knowing how to relate the equations that are given to you. And when we plug everything in, so we'll plug in V, D, and K, you should get around 188 volts per meters. So closest to that is 190. We're rounding up to 190. Okay. So the next question, the effective area of each plate of a parallel plate capacitor is 2.1 meters squared. 2.1 meters squared. The capacitor is filled with neoprene rubber with a dielectric constant, So our fancy K of 6.4. And we have a potential difference of 6 volts existing across the plates of the capacitor. And the capacitor is storing 4 microcoulombs of charge. We want to determine the plate separation of the capacitor. So first, we want to solve for our capacitance because we don't know it, but we do know that the equation is Q equals CV. We know Q, we know V, we can solve for C. So C will equal charge over voltage. We can plug in our numbers for that, over 6. And we also know that Q over V, and again, this is just another equation from the book from formula sheets, is equal to our dielectric constant, epsilon naught, times our area over D. So our dielectric constant was given to us as 6.4. Remember that E naught is a constant, and it's 8.85 times 10 to the negative 12. So I'm not sure which professors give that to you or not, but I would know that. And then once we plug in everything, we'll just set this 4 times 10 to the negative 6 over 6 equal to all of this. We have K E naught in the area, and we'll solve for distance. And when you solve for that, you should get, I got 1.8 times 10 to the negative 4. So letter C. So moving on to the next one, we want to determine the length of a copper wire that has a resistance of 0.172 ohms and a cross-sectional area of 7.85 times 10 to the negative 5 meters squared. And the resistivity of copper, so that's that like little p, it's called rho, is 1.72 times 10 to the negative 8 ohms times meters. Also, I forgot to mention before we started this whole thing, if people are like, oh, what is this from? This review is on this website, ucfsarc.wordpress.com. So my bad, I should have mentioned that earlier. So going back to this problem, we have an equation where we have, this is from chapter, I believe, like 22. R is equal to rho L over A. So we want to solve for the length of the wire, so we want to solve for L. So manipulating that equation will be L is equal to R times A over rho. And again, once again, like this is just another kind of plug and chug problem. We have the resistance, the area, and they gave us the resistivity. So that comes out to be 785 meters D. Okay. So, moving on to number 6, a 220 ohm resistor is connected across an AC voltage source, V equals 150 sine 2 pi 60t, where t is for time. And we want to know the average power of this circuit. So we know we have an R of 220 ohms, and we know V, they told us, is 150 sine 2 pi 60t. And before we can find the average power, we first need to find the V RMS. So remember that V RMS is just root mean square, so average voltage is equal to our V peak divided by square root of 2. So we know our V peak is that 150. So this will be 150 over square root of 2. So your V peak isn't this whole thing, it's just that 150. Because when we are at peak, this whole thing, this sine 2 pi ft will always equal 1. So always equals 1 at peak voltage. So when we do that 150 divided by square root of 2, you end up getting 106 volts. And now that's our VRMS. Now we can solve for average power, where average power, you can put the line over, you can say PRMS is equal to V squared RMS over R. So now we have that, and we have our resistance, and once you plug in those numbers, you should get 51 watts. So that's A. So just remember, you can use this. This is the regular power equation. You can just kind of, on your formula sheet, it says P equals V squared over R, but you can take it as also P RMS equals V squared RMS over R. So, cool. So, number 7, an electron is moving with a speed of 3.5 times 10 to the 5 meters per second. So it's always just easier to write out everything you know. And it encounters a magnetic field of 0.6 Tesla. So that's our B, our magnetic field. The direction of the magnetic field makes an angle of 60 degrees with respect to the velocity of the electron. So that's our theta, 60 degrees. And we want to know the magnitude of the magnetic force on the electron. So first, we know our equation for this is F equals QVB sine theta. The reason I know we need to use that equation is because we're looking for force and we're given literally everything else. So even if they didn't say theta, if they said just the magnetic field is perpendicular to the velocity of the electron, that theta would now be 0, and, or sorry, that theta would be 90, and sine theta would just be 1. Whenever you see velocity and magnetic field, you're probably going to end up using this equation. So we just basically plug everything in. We just want to find the force so we don't have to manipulate the equation at all. And that should give you 2.9 times 10 to the negative 14 newtons, which would be E. So just a plug and chug for that one. That one you just have to make sure you're using the right equation. So if we move on to the next one, and just let me know if I'm going too fast or anything. Number 8 is a particle with a mass of 6.64 times 10 to the negative 27 kilograms, and a charge of 3.2 times 10 to the negative 19 coulombs. Is accelerated from rest. So that means our V naught is equal to 0. And we have a potential difference of 2.45 times 10 to the 6 volts. The particle then enters a uniform 1.6 Tesla magnetic field. If the particle's velocity is perpendicular to the magnetic field at all times, so perpendicular, that means our theta will be 90 degrees. What is the magnitude of the magnetic force exerted on the particle? So this one is a little different because we have, we're given a velocity and a potential difference. I'm just going to move this kind of over here. We want to set our electric potential energy, which is our equation QV. So some professors write it like this: UE is equal to Q times V, our electric potential energy, is going to be equal to our kinetic energy, right? Because law of conservation of energy. And we are, what were we solving for again? The magnitude of the magnetic force exerted. So we are actually going to be solving for V. Yeah, because they didn't give us the velocity. So that's what we need to solve for. And when we manipulate this equation, we'll end up getting square root of 2qv over m. And that gets us a velocity of 7.87 times 10 to the negative 12. And I think I might have accidentally combined problems on this one actually, because it's asking for the force, but I structured the answers like it was asking for the velocity. So let's just pretend this says what is the velocity of the particle. And if you wanted to solve for force, now we have the velocity. Force can just equal 1/2 mv squared. And you would just plug that velocity back in. We have the mass, and you would solve for the force. So that was my bad. So if this was asking, let's just say, what is the velocity of the particle? And then that answer to that question would be 7.87. So this should be meters per second. That one was a fail. I'm sorry. So on to the next one. Hopefully I didn't mess this one up too. So number 9, a transformer changes 120 volts across the primary to 1200 volts across the secondary. So that means V primary is 120, V secondary is 1200. If the secondary coil has 800 turns, so we know NS is equal to 800, how many turns does the primary coil have? So that we're looking for NP. So these equations are in the book. We know that IS over IP is equal to VP over VS. And VP over VS is also equal to NP over NS. So we see that current and voltage are going to be inversely proportional, and voltage and number of turns are directly proportional to each other. So at this point, we can just plug things in. I mean, if we didn't have voltage, instead it gave us the current, then we would just pretend that's not there and set these two equal to each other. But we have voltage in turns, so we will just do 120 over 1200 is equal to, we're looking for NP over NS, which is 800. And I ended up getting 80. So NP would be 80 turns. So that'd be B. Okay. So moving on to number 10, a 250 turn solenoid carries a current of 9 amperes. So N is equal to 250. Our current is 9 amperes. So right when you see the word solenoid, you should know which equation correlates to solenoids, and that equation is B is equal to mu naught little n I. Or this is the same thing as saying mu naught capital N over L I, because this little n is just turns per meter, turns per unit length, and the big N is just turns, so if we want to plug that in, we have to do it over the length. Okay? So if you don't know which magnetic field equations go to solenoids, wires, coiled wires, I would make sure you knew that before the final. So continuing with this one, we have 250 turns, a current of 9 amperes. The radius of the solenoid is 0.075 meters, and its length is 0.14 meters. It says determine the magnetic flux through the circular cross-sectional area at the center of the solenoid. So it tells us it's circular, so we know the area will be equal to pi r squared. So if they said the square cross-sectional area, we would have to then use the area of a square, which is just L squared. Okay. So we can't really solve for flux yet. We need to find the magnetic field first. So remember that flux is equal to B times A. So we have everything we need for B. We have mu naught is our constant, the 4.47 times 10 to the 7 pi. I actually don't think that's right. I just blanked on the mu naught constant. 4 pi times 10 to the negative 7? Yeah. So that will be plugged in for our mu naught. We don't have little n, but we do have our big N and our L, so we can use this equation and plug those in. So really, we can just say flux is equal to mu naught N over L I times A. So everything else we can just really plug in. Just remember for the area, you can't just plug in the radius. This will be mu naught N over L I, and this area will be pi r squared. Okay, and doing that math out, I got it to be 3.6 times 10 to the negative 4 Webers. So make sure you know all of the units for everything, just because for the free response, and I do have free response at the end of this, if you don't write units, you're probably going to get points off. So it's a pretty easy thing to mess up on, but it's also a pretty easy thing to remember, so just make sure you know those units. So flux is always in Webers, WB. Okay, so are we good? I'm going to move on to the second page. So number 11, we have two 3.25 microfarad capacitors. So C is equal to 3.25 microfarads. Are connected in series, so that's important, across the terminals of a 50 hertz AC generator. So our frequency is 50 hertz, and has a peak voltage of 244. That should say 244 volts, but. Determine the RMS current in the circuit. So first, we want to find the VRMS, because right now we have the V peak. We can't find the RMS current without the RMS voltage. So remember that VRMS is equal to V peak over square root of 2. And we have the V peak, so that'll be 244 over square root of 2. And I'm actually not sure what exactly that comes out to. But if you continue, this is chapter 23 question. So we know there's an equation from chapter 23 that's IRMS is equal to RMS is equal to VRMS over R squared plus XL minus XC squared. So basically this whole thing is just equal to I equals V over Z, which is basically just a derivation of Ohm's law. So just kind of a side note, remember that for chapter 23 you have V equals I Z, V equals I XL, V equals I XC. To find, that's how you can find voltages across certain elements of the circuit. But in this case, it just wants us to determine the RMS current. So we have this all set up. We have VRMS. I don't believe we have a resistor at all. So this R will just be 0. And it looks like we also don't have any inductors or anything. So remember, when they don't say anything about it, you can assume that it's not part of the circuit. So since we don't really have any inductors, we can just plug in 0 for XL. For XC, though, we do have capacitors. So we just want to use our XC formula. I'm just going to move it over here real quick, which is equal to XC is equal to 1 over 2 pi FC. But first, we have 2 microfarad capacitors, and they're connected in series. So we kind of have to go all the way back to chapter 20, where we have to remember how to add capacitors in series versus in parallel. So remember, for capacitors in series, you do 1 over C1 plus 1 over C2 and on to the negative 1. And when they're in parallel, you just do C1 plus C2 and on, however many you have. So remember, it's the complete opposite from resistors, where with resistors in series, you just do R1 plus R2 plus R3. In resistors in parallel, we have R1, 1 over R1 plus 1 over R2, and so on. So just something to kind of remember, that they're different from from resistors. We can't just add them together in series. So once you get that total C equivalent from adding 1 over 3.25 plus 1 over 3.25, then you can plug that equivalent capacitance into the XC formula, solve for XC, and then we can come back over here and plug in that XC. So we want to break it down into steps. I mean, this doesn't really have to be your first step, but it's kind of the easiest step. First step to find VRMS. Second step to solve for the equivalent capacitance over the circuit. Third step to plug in that capacitance into our XC formula. And then finally, your fourth step would be to plug it into the whole thing, where I got 0.125 amperes, so E. So then, since those capacitors are in series, they both have that same current. So just kind of remember that. Let me leave that up there for a second. So moving on to number 12, this is probably a good concept question. I could see maybe Conacher possibly putting, because I did get these from his problems. So it's asking which of the following graphs shows how inductive reactance varies with frequency. So the first kind of step of this problem is knowing the equation for inductance, or capacitive inductance. We have XL is equal to 2 pi FL. And just for fun, let's put XC, we know, is 1 over 2 pi FC. So when we look at this equation for XL, we see that if we increase frequency, the XL will also increase. So they're going to be directly proportional. And then we see, just looking at XC for a moment, if we increase the frequency here, our XC will actually decrease, because if we increase the denominator, we're going to get a smaller number. So if we do 1 over 2 versus 1 over 100, 1 over 100 is going to be a smaller number than 1 over 2. So that's kind of basically what we're doing here. So XL in F will be directly proportional, XC in F will be indirectly. So if we just look at these graphs over here, we can see that in C, as F increases, so does XL, and that's correct. So our answer will be C. We also see here, just kind of pointing it out, this would be the graph of the capacitive reactance, where as we increase frequency, our XC will decrease. So this is the graph of XC. And then also for graph A, this is actually going to be the graph of resistance, because resistance does not, it's not affected by the frequency at all. Resistance is just resistance. And then just kind of so you can recognize it, this graph B is the graph for impedance, Z. And then honestly, this graph, last one, I'm not sure what that is. I don't think that's a graph or anything, but yeah. So just like being able to recognize those graphs, that's a good concept question you could be asked. So number 13. A series RCL circuit is operating at 60 hertz, so that's our frequency. Contains a 49 ohm resistor and a 5 microfarad capacitor. If the power factor of the circuit is +1, so power factor is +1, what is the inductance of the inductor in this circuit? So we want to find L. So first thing is we need to know what the power factor is. So it's in the equation for power. So we have P is equal to I squared RMS Z cosine phi, or phi. And this cosine of an angle is your power factor. So basically, we need the power factor of the circuit to equal 1. So we know cosine at 0 is going to be 1. So we need that phi to equal 0. So we're actually going to use another equation also from this to kind of relate it. So we know tan phi is equal to XL minus XC over R. And phi needs to be 0. So this is basically saying tan 0 and tan of 0 is 0. So it's just unit circle. Tan is cosine over sine, So when we see that tan is equal to 0, tan 0 is equal to 0, that's saying XL minus XC over R is equal to 0. So when we say that, that's basically just telling you that XL is going to equal XC. So if you want to just kind of remember that, when a power factor is 1, your XL and your XC will be equal. So if we know XL is equal to XC, we know that 2 pi FL will equal 1 over 2 pi FC. And we have everything we need to solve for our XC over here. So we have 2 pi, our frequency is, our frequency is 60 hertz. We have a capacitance of 5 times 10 to the negative 6 farads. and we would just solve for L. In doing that, we should get an L of 1.4 henries. So that'll be B. So just remember, you can relate those power factor equations. We know power factor is the cosine phi, so we can use tan phi to relate back to cosine phi. They solve for kind of different things, but that phi is going to be like kind of the same thing. Whatever you get for phi and cosine, we know it'll be the phi also in sine, or sorry, tan. Okay. So if we move on to 14, oh, that's not, okay, so EM waves are radiated uniformly in all directions from a source. The RMS electric field of the waves is measured 35 kilometers from the source to have an RMS value of 0.012. So our ERMS, newtons per coulomb. And that is, that is going to be 35 kilometers away. So first, we want to find, what is it asking? Determine the average total power radiated by the source. So we know that we have the formula S is equal to P over A. So intensity is equal to power over area. And this is also equal to C. So C for the speed of light times epsilon naught E RMS squared. So we were already given our E RMS. E naught and C are both constants. C is the speed of light, 3 times 10 to the 8 meters per second. And then really we can just plug everything in. Our area, just remember that, say that over here, this is our source. It's saying our EM waves, they're always going to radiate uniformly in all directions. So it's kind of like, this is the source. Our EM waves are coming out like this. And we're saying that the radius of that is 35 kilometers. Okay. So just remember that you're going to have to use that 35 kilometers, which is really 35 times 10 to the 3 meters, and plug it in to area is equal to pi r squared. Just be thinking about that. So determine average total power. We have E squared RMS. Again, these are constants. We can solve for the area, and we would just be solving for power. So it'd be P over A is equal to C E naught E RMS squared. And when I did that, it came out to be 5.9 times 10 to the 3 watts. Okay. So moving on to number 15. An EM wave has an electric field with a peak value. So now we have a peak electric field of 250 newtons per coulomb. What is the average intensity of this wave? So basically we can still use the same formula that we were just using, where we have intensity is equal to P over A, but it's also equal to C epsilon naught E squared RMS. So we're using the same formula, but now we have the peak value of the electric field. We don't have the RMS. So now we have to solve for the RMS value of that electric field first, which I would just kind of memorize this. I don't know if this is on formula sheets or not, but I know it's in the book, where you have your ERMS is equal to your E peak over square root of 2. So this will be 250 over square root of 2, which I'm not sure what that comes out to. Probably like a little over 200 or something. But once you solve for that ERMS, you can plug it in here along with your speed of light and your epsilon naught. We're not going to be worrying about power over area in this equation, and we'll be solving for our intensity. And I got that to be 83 watts per meter squared, so C. So 23 has a lot of different equations. Just remember that they can all basically relate to each other. There's a lot of equations in chapter 23 that can solve for the same thing. It just kind of depends on what you're given. Okay. So we're good with that one. So we can move on to number 16. If this will focus. So number 16, a woman stands 2 meters in front of the convex mirror and notices that her image is, that says 1/4 of her actual height. Determine the radius of curvature of the mirror. So we have a convex mirror, and she is standing 2 meters in front of it. She notices that her image height is 1/4 of her actual height. So this phrase, image height 1/4 of her actual height, is basically saying HI is equal to 1/4 HO. Height of the image, height of the object. And we want to determine the radius of curvature. So we know HI, DO is equal to 2 meters. And remember that the equation for radius of curvature is F is equal to -1/2 R. So remember, -1/2 R is for convex mirrors. So if we had a concave mirror right here, this would be positive, it wouldn't be negative. So just remember that. Usually concave is positive and convex is negative. So we know that we have the kind of expression HI over HO is equal to -DI over DO. And using this, we can actually solve for the distance of the image, because we see that we have a relationship between HI and HO. So HI, we can say 1/4 HO over HO. So now those HOs will cancel. So after that, we just get 1/4 is equal to -DI over DO. We have the distance of the object is 2. So now we can solve for DI. And that DI is going to be -0.5 meters. And that negative is telling us that our distance of the image is behind the mirror. So this is our distance of the object, the woman, and this will be our distance of the image, and this will be approximately like 0.5 meters. But the question wasn't asking for the distance of the image, it's asking for the radius of curvature. So in order to find that R, we first need to find the focal point, or the focal length. So now that we have DI, DO, we can now solve for the focal length, where we have 1 over DO plus 1 over DI is equal to 1 over F. And we will just be plugging numbers in. For these questions, make sure you also carry over the sign. So since di is negative, it's basically going to be 1 over do minus 1 over di. So I'll plug that in, kind of running out of room. So this will equal 1 over 2 minus 1 over 0.5. And when I did that, I got F. So remember that equals 1 over F. I got F is equal to negative 2/3, which this makes sense because focal lengths for convex mirrors are going to be negative. So you should be getting a negative for that. So once we have the focal length, now we can basically multiply it by negative 2 to get our R. So we're going to plug that in. Negative 2 over 3 equals negative 1/2 R. And I got 1.3 meters for the radius of curvature. Okay. So all of the equations kind of for this chapter, mirrors and also lenses, are kind of like simple, but it gets kind of complicated, you know, once you get here, because they all can relate to each other and you just kind of have to find those relationships. Okay. So moving on to number 17. So an object is placed 20 centimeters in front of a concave mirror now, a concave spherical mirror that has a radius of curvature of 60 centimeters, and we want to know which of the following is true. So I always just kind of draw these out. It kind of helps me to draw it out. So we have a concave now. Our DO is 20 centimeters away. And basically all of these answers are saying, is the image real or virtual, and where is the image located? So we want to solve for DI. So we know 1 over DO plus 1 over DI is equal to 1 over F. And this question gave us the radius of curvature. So we can solve for F knowing that radius of curvature. So I said F is equal to 1/2 R. So half of 60, F should be 30 centimeters. Going on, so now we have DO and we have F, so now we just need to find DI. So we have 1 over 20 plus 1 over DI is equal to 1 over 30. And when I solved that out, I got DI is equal to negative 62.5 centimeters. Okay. So we can kind of cross some things out. We know it's going to be located about 60 centimeters away from the mirror, so we can cross out A, C, and E. So it's got to either be B or D, so basically we just need to figure out if the image is real or if it's virtual. So this negative right here in the DI tells us that the image is virtual because it's behind the mirror. If it was in front of the mirror, then it would be real. So that would be D, the image is virtual and located 60 centimeters from the mirror. Okay. So going on to number 18, a charged particle is launched with a velocity of 5.2 times 10 to the 4 meters per second at an angle of 35 degrees. So that's our theta, with respect to a 0.0045 magnetic field, Tesla magnetic field. If the it's kind of hard to see on there. If the magnetic field exerts a force of 0.0026 newtons, so that's our F, on the particle, determine the magnitude of the charge on the particle. So we're looking for Q. So here we have an F, we're looking for Q, we have a B, we have V, and we have a theta. All of this together should tell you that we are going to be using F is equal to Q, B, B, sine theta. So we should be using that equation, just because we have all the variables for it. So yeah, and then we can just plug everything in. Q will equal F over V, B, sine theta. We have our force, we have velocity, magnetic field, and our angle, so we can just plug everything in, and we should get about 19 microcoulombs. Let's see. Okay. That one isn't too bad. Moving on to 19 and 20. So in 19, a 4 ampere current is maintained in a simple circuit with a total resistance of 2 ohms. How much energy is delivered in 45 seconds? So you can basically think of power and energy. They're not exactly the same thing, but they're very closely related. So we know power is equal to I squared R. And we know that energy, and I know we don't really use this equation too much, so you kind of forget about it. Energy is equal to power times time. So it gives us what we need to solve for power in general. And we have a 4 ampere current and a resistance of 2 ohms. So that'll be 4 squared times 2, which that's 4 squared is 16 times 2, that's around 32 watts. And then we can use this power to solve for the energy. So we want to know how much energy is delivered in 45 seconds. So we'll just end up doing 32 times 45. Because remember, seconds is our SI unit for time. And I believe you should get around 1440 for that. So, and there's another question like this I got a question about from Saha's practice problems. We're asking how much energy is within this given amount of time, not per unit of time, so we're not going to be dividing. This isn't going to be watts per second. It will be watts times second, which is another way of saying joules. So if it's asking how much energy is delivered in this given amount of time, you're going to multiply. If the question is asking, you know, how much energy is being delivered, let's say like it said per week, then you would have to do the conversion and divide, because it would be asking per unit of time, not in a certain amount of time, if that makes sense. And then this is the last question for the multiple choice section. So 20, we have a negative 4 microcoulomb charge. So I'm going to draw this out. We have a negative 4 microcoulomb charge located 0.45 meters to the left of a positive 6.0 microcoulomb charge. And we want to know what is the magnitude and direction of the electrostatic force on the positive charge. So this should kind of show you right away that we're going to be using good old Coulomb's law. So don't forget about Coulomb's law. F equals KQ1, KQ2 over R squared. So remember our regular K, this is not we have this K, and then we also have dielectric constant. Just make sure you kind of don't get them confused. This K is 9 times 10 to the 9. That doesn't look like a 9. 9 times 10 to the 9. And then we can really just plug this in, all of our stuff in. Remember to take the absolute values of your charges. And we should get a force of 1.1 newtons. So that kind of helps us narrow it down a bit. So we can cancel or cross out A, B, and E. But now we have to figure out which way this force is moving. So remember that it's asking what is the magnitude and direction of the electrostatic force on the positive charge. So since we have a negative and a positive, those two are going to be attracting to each other. So where's the force going on this positive charge? It's going to be going to the left. So it'll be D. So if we were talking about the negative charge, then we would get 1.1 to the right. Okay. Does anybody have any questions on the kind of like multiple choice part before we go into the free response? If anybody wants to see, like, if they came here late, wants to see the previous problems, just let me know. But if not, we can go ahead and go on to the free response section. So in the first question, we have a disk with a radius of 0.1 is oriented with its axis at an angle of 30 degrees to a uniform electric field. So let's go ahead and just write down some of the stuff we know. We know the radius is 0.1 meters. We know an angle is 30 degrees with respect to an electric field. And we know that the electric field is equal to 2 times 10 to the 3 newtons per coulomb. So it's always just easiest to like write what you know right away. So A is asking, what is the total electric flux through the disk? So remember, I'm just going to write A here, that flux due to electric field. So we have flux due to magnetic field, and we also have flux due to electric field. Flux due to electric field is basically kind of the same formula as with magnetic field, but instead of B, you're going to use E, because we don't have a magnetic field this time, we have an electric field. So flux equals EA cosine theta. I'm going to draw a little picture just kind of help. So let's say this line here is our electric field, and we have a disk. What did it say? A disk is oriented with its axis at an angle of 30 degrees to the electric field. So let's say this is our axis, and this angle will be 30 degrees. So if you want to draw the disk as well, it'd be kind of like this, like a disk tilting through an electric field. So that's what that's going to look like. And then really we can just kind of plug and chug. We know the flux our electric field is 2 times 10 to the 3 newtons per coulomb. Our area, it's a disk, so we're going to use our area as pi r squared. So pi 0.1 squared. And in this case, they gave us the angle, so we'll just do times cosine 30. This is like, okay. So another kind of plug and chug thing. So that gives you, I got 54.41 Webers. This is not focusing very well. Okay. So I got 54.41 Webers for that one. It was kind of easy. They gave us everything we needed to know. But we have 2 more parts. So B, what is the total flux through the disk if it is turned so that its plane is parallel to E? So this time its plane is parallel. So let's go ahead and kind of draw what that's going to look like. So now we still have this same electric field, but now we're going to turn this disk so that the flat side is parallel. So you see that? So another way of kind of saying this is that its axis is perpendicular. And saying it kind of that way helps you realize what theta this is actually going to be. If we see, because in part A, our angle, oh my goodness, our angle was relative between the electric field and the axis of the disk. So now in B, we're still going to use that same kind of way of thinking about it. We're going to say that angle is still the angle between the electric field and the axis. So when we say that, we'll get the theta is equal to 90 degrees. This thing is like going crazy right now. So we're still going to use the same formula. We'll do phi, or flux, is equal to EA, but now it'll be cosine 90. So really don't have to do any calculations. We know cosine 90 is always going to be 0. Remember that unit circle. So the total flux through this will just be 0 Webers, and that makes sense because if you're turning this, this disk so that the electric field can't go through the area of the disk. So there's nothing going through, kind of like, if you think of a hula hoop, nothing's going through the hole of the hula hoop, so nothing can happen. There's no flux going to be happening. So the last part of this question, part C, is asking what is the total flux through the disk so that its axis is parallel to E. So now we're saying our axis is parallel. So let's draw this out. We have the same electric field, but now we're going to draw it so that our axis is going parallel to that. So now if we look back at B, we said that this was 90 degrees. So over here, now the axis, there's no angle between that. So that's going to be, our theta will be 0 degrees. And we know cosine at 0 is just 1. So basically you can just say phi is equal to E times A. So that'll cancel out to be 1. And then when I calculated that, I got it to be 62.83 Weber. So this is kind of like max electric flux because this is when you have the total amount of electric field going through that area of the disk. Is that good with everyone? So drawing pictures always helps. 10 out of 10 recommend doing that. So if nobody has any questions on this one, we can go to number 2, where this is actually a question taken from Dr. Saha's practice problems. We have a positive point charge, so Q is 7.2 times 10 to the 8 coulombs. It's surrounded by an equipotential surface A. So remember way back to the beginning of the class, equipotential surface means we have the same potential over the entire surface. There's no change. And this surface A has a radius of RA of 1.8 meters. RA is equal to 1.8 meters. And then a positive test charge is 4.5 times 10 to the negative 11. So I'm going to label that as Q naught, 4.5 times 10 to the negative 11 coulombs. Moved from surface A to surface B which has a radius RB. So I think that's what we're going to end up solving for. So we don't know what RB is. And then it tells us the work done as the test charge moves from surface A to surface B. And they give us a work of negative 8.1 times 10 to the negative 9 joules. Okay, so they gave us a lot of information, so let's draw this out. We have surface A. We have surface B. And we have this point charge in surface A. So this point charge is not moving. So I'm just going to write Q there for our point charge. And then we also know, I'm going to kind of move this. RA is 1.8 meters. We're looking for RB. So now we have this test charge going from surface A to surface B. So that's kind of what's happening right there. So that's kind of just a picture of what's happening. They give us the work. So that should kind of like jump out that you're going to have to do something with potential energy. So we know the change in potential energy or electric potential energy is equal to negative work. And we know this. We can kind of rewrite this as saying VB minus VA is equal to negative work over Q naught. Because that's really what's happening. We're going to use that test charge because that's the one that's moving, and that's the one that is actually doing work. The point charge isn't doing any work because it's not moving at all. So I kind of made like a jump here. Just remember that electric potential energy is V times Q. So I just factored out that Q and divided because this is going B and A. Let me actually just redo this. So we have Q naught VB minus Q naught VA is equal to negative work. Factored out this Q because they're both, this is what they have in common is that test charge. Factor it out and divide it, and then we can get VB minus VA is equal to negative work over Q naught. So maybe that might be like a little easier to follow. So now we kind of have this equation, but we don't have the velocity, or I keep calling it velocity, the voltage of either of these. So we kind of have to go back and remember the equation for voltage, which if you guys remember, it's V is equal to KQ over R. So we're going to plug each of these in for both of those. So we'll have KQ over RB minus KQ over RA, and I'm just going to go ahead and plug in 1.8 for that. And when we plug in our work, which is already negative, into negative work, we're going to get positive. So that'll be positive 8.1 times 10 to the negative 9 joules over our test charge of 4.5 times 10 to the negative 11 coulombs. So we're going to plug everything in. Remember, K is just our constant. For Q of RB, we're going to use the test charge Q naught because that's the only charge that's kind of happening at RB. So I'm just going to plug that in. 4.5 times 10 to the negative 11 over RB is what we're solving for. And then for RA, we're going to actually use the point charge because we need to accommodate for this point charge that's happening. So if you see so far, we have not done anything with that point charge, so we need to plug that in here to kind of show what effect that point charge is going to have on the work. So that point charge, 7.2 times 10 to the 8, all over 1.8 is equal to all of this. Sorry, my phone went off. So you just kind of have to do a lot of algebra. You have to solve for this part. You'll get a number for this to where you can get KQ over RB. You get E is equal to 540. And just doing that math out, I got RB to equal 1.2 meters. So that's like a decent number for that value. So whenever you really see work, you're most likely going to be using something with electric potential energy. It's probably just usually a good rule of thumb. So we plugged in our QV, our change in QV for the change in electric potential energy is equal to our negative work. Factored at the Q naught because that's what they both have in common. Q naught is going to spend time at both of these equipotential surfaces. So VB minus VA will equal that negative work over our test charge, and then we can use this equation to plug things in and solve. So how does everyone feel about that? So a lot of kind of jumping between equations. Okay. So we can move on to the next one. Oh, yeah. I can zoom out a little bit for you. It goes out of focus like every time I touch it. So the next question, we want to find the equivalent resistance. So yeah. So first thing, whenever you want to find the, what the heck? Whenever you want to find the equivalent resistance, we kind of just want to break down this circuit all into one resistor. And we'd do the same thing if they were capacitors. I don't understand why this is happening. Okay. We're going to break this whole thing down basically into just one resistor. Same thing if they were capacitors, we would just add them up differently. So let's go ahead and start. I like to start from right to left. I think it's just easiest. There's probably ways to do it otherwise, but this is just the easiest for me. So we see that this 1 ohm, 2 ohm, and 3 ohm resistors, they are all in series because they don't have any junctions between them. When we go through this 1 ohm resistor, we are forced to keep going through the 2, and we go through the 2, we are forced to go through the 3. Versus if you see here at the 6 ohm, if you see the 6 ohm, we're not forced to go onto the 1 ohm resistor. We could either go to 1 or we could go to this 3 ohm. So these are not going to be in series, but these last 3 will. So remember, when adding resistors in series, we can just add them up. So I'm going to draw kind of a new circuit. So this is A, B, so now we can add these 1 plus 2 plus 3 is 6, right? Yeah. So these are all going to be added up into one 6 ohm resistor. So now we have this 3 and the 6 ohm in parallel. I like to kind of draw it at the like where this 2 would be, just because it's easiest to see that they're actually parallel at that point. So we know when we add resistors in parallel, we need to do 1 over 3 plus 1 over 6 to the negative 1. And when I calculated that out, I got it to be 0.5 ohms. So we're going to break this down again. And we can't include that 6 because of that junction between 6 and 3. So this will be our new resistor, 0.5 ohms. This one is 6 ohms, 4 ohms, 2 ohms. So now we can add these two in series because there's no junction between them. So now you get this 2 ohm, 4 ohm, and these will just add up together to get 6.5 ohms. And then once again, we have two parallel resistors, so we have to do 1 over 6.5 plus 1 over 4 to the negative 1. Remember, you don't forget that negative 1 because the actual equation is like 1 over R equivalent is equal to 1 over R2, or 1 over R1 plus 1 over R2, and so on. So if you don't take that negative 1, you didn't solve for R equivalent, you solved for just 1 over R equivalent. So make sure you do that. So when we do this, so this is A, B, we still have that 2 ohm resistor. When I added those up, I got 0.4 ohms. Now this kind of last step, you don't actually have to ever draw it out into one resistor, but we have 2 plus 0.4, so our total R equivalent will equal 2.4 ohms. So if you have like kind of a question like this on your exam, I always like recommend just drawing everything out. It's the easiest way, and that way you get maximum partial credit if you accidentally mess up on the way. So yeah, just remember to break things down. When we do this, if we had a battery or a generator or something attached to this, this is when we can, once you break down everything and find the total R equivalent or the total current through the circuit, that's when you can build circuits back up and find, you know, like a specific current or voltage at each of these resistors. So yeah, so just remember some things with circuits to kind of go over. Just remember when we're in series, we will have the same current, and we will add R1 plus R2 plus R3 and so on. But we will add capacitors as 1 over C1 plus 1 over C2 plus 1 over C3 and so on to the negative 1. And remember, when we are in parallel, we have the same voltage across the elements. And it's just the opposite. We have 1 over R1 plus 1 over R2 and so on to the negative 1, and we can add capacitors. Just adding. So don't forget about that kind of stuff. I know it was like a while ago and you might not have used it for a while, but that's important. So moving on to number 4. Oh, yeah. Oh, yeah. I can't really fit like the whole thing up here, but if you want to like take a picture of it after, you can also do that. I can't. So are y'all good with this? Or go, take your time. Good? So moving on to number 4. I'll zoom this in a little bit. So when a charged particle moves at an angle of 25 degrees with respect to a magnetic field, it experiences a magnetic force F. At what angle that's less than 90 degrees with respect to this field will this particle moving at the same speed experience a magnetic force of 2F? So let's just kind of write down what we know. We know when we're moving at 25 degrees, we have just regular F. We have one F. And we know at some other angle, we can call it theta 2, we are moving at 2F. So a good thing to note is that it says blah, 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 moving at the same speed. It kind of addressed that. And we have the same magnetic field. So when they said the same speed, that was kind of like a red flag to use this equation, F equals Q BB sine theta. And that's kind of one of the few force equations that we have with an angle in it. I can't think of anything else right now on the top of my head that also has theta in it. So that was also a red flag. So we want to kind of get this equation in terms of force and of theta. And we know it's the same particle. A charged particle moves at this. So we're keeping the same particle moving. So we have the same Q. We're not changing the charge at all. And they told us it has the same speed. And it's also going to be in the same magnetic field. Oh my goodness. So we can basically say, if you think about it like F over Q V B sine theta is equal to F over Q V B sine theta. That Q V B, they're all the same. They're going to cancel out. So let's kind of get this in terms. We know that we have one F when we're traveling at 25 degrees with respect to the field. And we'll put a 1 in front of this. And then we're moving at 2 times this force when we're at some angle. So if you notice, we don't have an actual number for force. We could say that, this force is 1 Newton, and when we're at 25, we have 1 times 1 Newton of force, and when we're at this angle, we have 2 newtons, because 2 times 1. So this F is the same number, so those F's can also cancel. Okay, so we end up getting 1 over sine 25 is equal to 2 over sine theta. And now we can just solve for theta. And I got, when I calculated this out, to be theta is equal to 57.69 degrees. An easier way to kind of solve for this, I just took the inverse of both sides. So we have sine 25 over 1 is equal to sine theta over 2. So sine theta will equal sine 25 times 2. And then you can do the inverse sine of that. Okay. And that should be 57.69 degrees. So, we all good with that one? Yeah, not too bad. So going on to number 5, a 120 volt motor draws a current of 7 amperes when running at normal speed. The resistance of the armature wire is 0.27 ohms. So the first thing we want to do is determine the back EMF generated by the motor. So we know we have V equals 120 volts and an I of 7 amperes, and this is at normal speed. And we have a resistance of the armature wire at 0.27 ohms. The first part of this is asking to determine the back EMF from the generator. So we actually have an equation for this. It's kind of a derivation of Ohm's law, where we have I is equal to V minus R epsilon over R, and epsilon is just EMF. So remember that the back EMF is kind of another voltage that is created by the generator generating another voltage. So we kind of have, like when we say we have a voltage of 12 volts, but it's really a little less, because this back EMF is kind of taking away from that. So we really can just plug and chug in this one. They gave us the current to be 7 amperes. So we'll do 7 equals, our voltage is 120. We don't know the back EMF, and our resistance is 0.27. So when I calculated that out, I got 118 volts for our back EMF. So we're saying the voltage is like 120, but really it's a little less than that because of this back EMF. Okay. So the second part of the question B, what is the current at the instant when the motor is just turned on and has not begun to rotate? So that phrase, has not begun to rotate, should tell you that since this motor has not begun to rotate, that's what's generating the back EMF. So if we have no rotation, we have no back EMF, and that EMF will just be 0. So when you do this part, we're going to use the same exact equation, but now that'll be 7. It'll be 120 minus 0 over our 0.27. Because it's just beginning to start, we haven't kind of created a back EMF yet. And I got like 444. Sorry. I was looking for the current. So I got 444 amperes for that. So pretty big number. Okay. And the last question for this question, what series resistance must be added to limit the starting current to 15 amperes? So now we have kind of a new current that we want to test. So we're really going to be using, again, like the same exact equation. But now we're going to be looking at 15 amperes. So when this says what series resistance, that's giving you a hint that our R equivalent is just going to equal R plus R, R1 plus R2. Oh, sorry, I can't see that. So once again, we're going to be using the same equation. We're just going to have our 120 volts. We're not going to take into account a back EMF for this one. And we're going to add a resistance to our 0.27 resistor that we already have in the circuit. Okay, so we'll just be solving for that R, and whatever you get for that will be your answer. I got it to be 7.73 ohms. So that means we would have to add 7.73 ohms of resistance in series to this current 0.27 to get our current to 15. They could have asked, it's a little more complicated, but if they would have asked what parallel resistance must be added, I personally, so let's just say in case of parallel, I would have personally just done 15 is equal to 120 over REQ, solve for that REQ, and then do this 1 over R1 plus 1 over 0.27 to the -1. That would just be a lot easier. Since they said it was in series, it wasn't too hard just plugging it into the equation. But if they said parallel, that's personally what I would do. Okay, so is everyone good with that one? Cool. So going on to number 6. in a series circuit, a generator that is 1350 hertz and 15 volts is connected across a 16 ohm resistor, a 4.1 microfarad capacitor, and a 5.3 millihenry inductor. Find the voltage across the inductor. So just seeing all these different elements of the circuit should tell you that this is most definitely going to be a kind of a chapter 23, at least in the book I used. I know there's different books, but the RLC circuits. So we want to find the voltage across the entire inductor, my bad. So first thing we want to do is kind of solve for the impedance. So we know the impedance is equal to our R squared plus XL minus XC squared. And in this case, we have all of the elements. We can't just plug in 0 for any of these. So we will have to, and I don't have the actual answer for this one, so we'll have 16 squared plus XL minus XC squared. Remember, so we don't have XL and XC. We have the capacitance and the inductance. These are both inductive reactance and capacitive reactance, so you'll have to solve for 2 pi FL and our XC to be 1 over 2 pi FC, where our L is 5.3 times 10 to the negative 3 henries, and our capacitance is 4.1 times 10 to the negative 6 farads. So I don't actually have all of that calculated out, but you will just plug these in to both of these elements, and then whatever you get for these, you'll plug into the impedance. And once you have that impedance, we're going to use a derivation of Ohm's law. Remember that I showed earlier V is equal to I times Z. And since these are all in series, remember they're all going to have the same current. So we want to solve for the current after that. So the current will equal your voltage over your impedance. You can find that. And last step, they're just asking for the voltage across the inductor. So once we have this current, the current will be the same at the inductor, just like it will be the same at the capacitor and the resistor. We are going to go to this equation, V equals I XL, where we already solved for XL, so we'll plug that in here, and we just solved for the current, and we'll plug that current into here. And solve for and that'll give us the voltage just across the inductor. When I did the whole thing, I got 29.6 volts. So you could have done that with anything. If they asked for voltage of the capacitor, it would be V equals IXC. If they asked for the voltage across the resistor, V equals IXR. You could have solved for the voltage across the entire circuit, where you would have used V equals IXC. And my bad, I forgot to mention that they gave us the voltage here. So never mind. You couldn't have solved for the voltage of the whole thing because they gave you the voltage of the whole thing. That kind of makes sense. I didn't do all of the math, but it's just a lot of plugging in the calculator. So make sure you know these. Is everyone good with this one? Okay. So if we move on to number 7, the average intensity of sunlight at the top of the Earth's atmosphere is 1390 watts per meter second. So that's our S, intensity. So we want to know the maximum energy that a 25 meter by 45 meter solar panel could collect in 1 hour of the sunlight. So you have a solar panel, just a square. So we have 25 meters by 45. So that's giving us our area of our panel. So our area will be 25 times 45. Did I do that? No. So I don't know what that comes out to, but we want to know the maximum energy. So remember that I said earlier, power and energy are very closely related. So we know we have S and we have A. So we know S is equal to P over A. We could solve for power doing that. When I solved for power, I got 1.5 times 10 to the 6 watts. So that's not our final answer yet. Oh, I guess I should probably make that a little clearer. So power is equal to 1.5 times 10 to the 6 watts, not the intensity. So now that we have that power, we did one question very similar to this one earlier. It's saying what is the maximum energy that this solar panel could collect in 1 hour of the sunlight? So again, it's asking for the amount of energy within a given amount of time. It's not asking per week or per hour or whatever. If it said per, you divide. But since it's not, it's saying 1 hour. We want to convert this into seconds because that's our SI unit for time. So I'll just kind of do that conversion. We have 60 minutes in 1 hour, and our hours will cancel out. And then we have 60 seconds in 1 minute. So this comes out to be 3,600 seconds. Okay, and then we're kind of going back to the equation. Energy is equal to power times time. And we have 1.5 times 10 to the 6 watts times 3,600 seconds. Remember, watts times seconds is equal to joules. That's kind of like a conversion between those two units. 5.6, and I got 5.6 times 10 to the 9 joules. So don't forget about that energy equation. Is everyone good with this one? So we have two more. Both kind of the last things you guys have gone over in this class. So number 8, a mirror produces an image that is located 34 centimeters behind the mirror when the object is located 7.5 centimeters in front of the mirror. So we don't really know, it's going to end up asking whether it's concave or convex, so I'm just going to kind of draw a line representing the mirror. And it says our image is located 34 centimeters behind. So DI, 34 centimeters. When the object is located 7.5 centimeters in front. So this is our DO. We want to know the focal length of the mirror and whether it's concave or convex. So this is kind of like a simple 1 over DO plus 1 over DI is equal to F. So just remember that when plugging this in, we're going to have a positive, we are going to have a positive DO because it's in front of the mirror. So we'll have 1 over positive 7.5. But this 34 is going to be negative because it's behind the mirror. So it'll be 1 over negative 34. So I know like you kind of got used to not including charges and just taking the absolute value of things, but now in this chapter we have to take into account those charges. And you set it equal to 1 over F. I got F to be 9.62 centimeters. And since that F is positive, that means it's going to be concave. If I got a negative 9.62, then it'd be convex. Okay. And then I believe this is actually the last question. So, and this is Snell's law. This is Snell's law question, if this will focus. So it says the drawing shows a rectangular block of glass, and it gives us the n equals 1.52. So I'll go ahead and write that in here. Surrounded by liquid carbon disulfide, where our n is 1.63. A ray of light is incident on the glass at point A with a 30-degree angle of incidence. At what angle of refraction does the ray leave the glass at point B? So really them giving you like these values of n should tip you off that this is a Snell's law question. And if you don't know Snell's law, that's n1 sine theta 1 is equal to n2 sine theta 2. And we're going to have to actually use this twice, because when we go in, we know that we have a 30-degree angle of incidence right here. So this is actually going to be forming a right triangle. And I wrote that in a poor place, but this is going to be forming a right triangle, and this angle at which the light is coming in to the glass. And the drawing doesn't show it very well, but remember that when you have light going into water or another substance, it's going to get diffracted a little bit, and it's not going to keep going in at that same angle. So even though it looks like they're congruent angles, they're not. I just can't draw. So our first act of doing Snell's law will be us finding this angle right here. Okay, so let's go ahead and plug this in. So N1 will be the N that we're starting in, which will be that 1.63. Sine our theta will be our angle of incidence. And then our N2, the light is now going into the glass, so our N2 will be our 1.52. And we're looking for this, theta 2. So I got this theta to be 32.42. So it's very close to the angle of incidence, but it is a little bit bigger. Kind of a good concept question that, or good concept to know, is that when you're going, how am I going to write this? When you're going from a bigger n to a smaller n, so in values, let me try to draw this decently. We're going in at this angle, and this is your angle of incidence. Your angle of refraction is going to be bigger than your angle of incidence. So instead of going towards the normal, you're going to go more away, if that kind of makes sense a little bit. It might make sense when you see the opposite. So when we're going from smaller n value to bigger, you have that angle of incidence, and your angle of refraction, that's not good, but will be kind of going closer to the perpendicular of the surface. So that's just kind of like side note. Bigger to smaller, you're going more away from the normal. Smaller to bigger, you're going to be going closer to the normal. The normal is just another word for perpendicular. So after that side note, going back to this, so we found the theta 2, and I'm going to kind of redraw this triangle out here, because it'll just be a little, so this is just this same triangle, where we have our 90-degree angle. This angle right here is 32.42 degrees. So we need to find this angle up here, because this is going to be the angle that the ray of light is leaving the glass. So we can just say that this angle will be 90 minus 32.42. because remember, back and trig, all of these angles will add up to 180. I kind of just disregarded this 90 because 180 minus 90 is 90. So these two angles over here need to add up to 90. So that's why I did that. And what did I get? I think looks like I got 57.58 degrees for that angle. So now that one is going to be our new in one because we have to do Snell's law again to get back out of the glass. So, second round of Snell's law. Now we're starting in the glass, so our N1 will be 1.52. And we're leaving the glass at 57.58 degrees. And now we're going back out to the carbon disulfide, so our N2 will be 1.63. And I'm running out of room. Sine theta. So now we just have to solve for that theta. I got that to be 51.9 degrees. And I can zoom this out so you can see the whole thing. So lenses and all in refraction, it's a lot of geometry, so if you're not comfortable with trig and like trig functions and drawing out triangles, I would definitely practice that before the final. Because I think for the most part, for most of the classes, you guys haven't taken a test on this yet, so. But that's the last of the problems. We have about 10-ish minutes left, so if anybody has any questions, wants to come up and see one of the previous questions and the answers, then we can do that. Good luck, everyone. You got this.